We're now going to take a look at differentiation and integration of exponential and logarithmic functions to any base a. So let's recall that an exponential function like a to the x can be written as e to the x times the natural log of a. So we saw that previously. And the logarithm to the base a of x can be written as the natural logarithm of x divided by the natural logarithm of a. So remember, these are both logarithms to the base e. So what we can do is we can use these two formulas to evaluate the derivative of a to the x and log base a of x for any base a. So we have this theorem here that evaluates those two derivatives for us. So for any base a greater than 0, the derivative of a to the x is the natural log of a times a to the x, and the derivative of log base a of x is 1 over the natural log of a times x. Keep in mind this natural log of a, that's just a constant number. So let's take a look at the proof of these two results and then we'll do some examples. So for the proof of number 1, note that we can write a to the x using this result right here. So there we just took the derivative of both sides here. That's essentially what we did. Now what we want to do is take the derivative of the right-hand side, and this is going to be a little chain rule problem where this is our u right here. So this evaluates as and now the derivative of u with respect to x, that's just going to be the natural log of a, because the ln of a is just a constant number. And the derivative of e to the u is just e to the u. All right, once again, derivative of x times ln a with respect to x is just ln a because that's a constant. Think of it like the number 5. Derivative of 5x is 5. And then substituting what u is back in here, we get and I just put the ln of a in front of the e to the u. And now keep in mind that this part right here, using this result again, that's just a to the x. And we get our result. And that's exactly what we have right here. Now let's take a look at the proof of part 2. Well, once again, just using this formula up here, differentiate both sides with respect to x, and we get now keeping in mind that the ln of a is just a constant number, we can move the 1 over ln a out in front of the d dx here. It's just a constant, so we can write that as and the derivative of your natural logarithm is 1 over x. And then just rewriting that as we have our result here. And so those are the proofs of part 1 and 2. Now take note of this. If the a in these two formulas is equal to e, well then this just reverts back to our derivative of the natural exponential and natural logarithm function. So notice if I put an e in place of the a here and here, we get d dx of e to the x. Well, that should be e to the x, and it is. Notice the natural log of e, putting an e in right here, ln of e times e to the x, that's just 1 times e to the x, keeping in mind that this is just 1 right here. And we recover the formula d dx of e to the x is e to the x. And the same thing for part 2. We recover the formula derivative of the natural logarithm is 1 over x. So notice if I put an e right here in place of the a here and here, this formula just becomes d dx log base e of x. Now log base e of x, that is the natural logarithm. And we get 1 over ln of e times x, but once again ln of e is just 1, and we recover the formula d dx of the natural logarithm of x is 1 over x. So these two formulas do agree with our prior results when a is equal to e. So let's take a look at this example down here. So let's evaluate the derivative of these two functions. First of all, 2 to the x. Well, following our formula right here, that's just simply going to be the natural log of 2 times 2 to the x. And there you go, it's as simple as that. Part 2, let's take the derivative of 3 to the sine x power. Now what we have to do here is we have to do a little chain rule problem. You see in the previous problem, you notice how the x right here and the x right here matched, as they should in our original formula over here. Well, here they don't match, so we have to use a little chain rule. So we have to let this be u, and we write this as and you see now this and this match, so now we can use part 1 right here, and we get our result. Okay, so this piece right here just became this part right here. And now du dx, u is sine, so du dx is going to be cosine of x. And then just substitute what u is back in here, and we get our final answer. And there's our derivative for 3 to the sine x power. So once again, notice how we had to use the chain rule. Now let's take a look at 2 more examples. I don't have them stated over here, but let's take a look at this one. Let's evaluate the derivative of this function. So derivative of log base 10 of x, well, we just have to use this result right here. Now notice here that the x's do match here and here, so we don't have to use the chain rule. We can just directly apply this formula, and we simply get, and there we go, that's our result. Let's take a look at one more. So here we want to evaluate log base 10 of the cosine of x. So notice here, this x and what we have in the parentheses here, they do not match, so we have to use the chain rule here. So we will let this piece cosine of x be our u, and so this will be now this part right here, we can just directly apply result number 2. Notice how the u here and the u here match, So we can just directly apply this formula, and we get that this is equal to now d du, derivative of cosine of x is negative sine x, and we get our answer. And there we go. Now let's look at some integration formulas. So here's an integral result that we have. Notice that since the derivative of a to the x power is ln of a times a to the x, we then have that the antiderivative of a to the x dx is 1 over ln of a times a to the x plus c. And notice we could also write that as so of course you could see it written like that as well. Let's just prove this result quickly. Well, to prove this, all we have to do is differentiate this side and show that we get back a to the x power. So just note that now the derivative of a constant is just 0, so this will just go away when I take the derivative of it. Also note that 1 over ln of a, this is just a constant number, so I can move it in front of the d dx, and we get this. So there, I just move the ln of a outside in front of the d dx, like this. And now this piece right here, so we're going to get, and this part right here is, as we've seen previously, that is this right here. And so the ln of a and the ln of a cancel, and we get a to the x. And there we go. So that proves that the antiderivative of a to the x is a to the x divided by ln of a plus c. Let's take a look at this example right here. So we want to evaluate the definite integral from 0 to 2 of x times 3 to the x squared power. Now with this one right here, you notice that if we look at the formula here, it doesn't quite match. You know, the x right here and the x right here, they don't match. I have an x and an x squared here, so we're going to have to use a substitution here. So for this problem, we're going to let u equal, well, let's try letting u equal the exponent right here. In which case then du is going to be 2x dx. So then this integral right here will become, now the 3 to the x squared, that's going to become 3 to the u. The x dx part, that part right there, well, looking over here, that's going to become du over 2, because if I divide this 2 under with the du, I get now the 0 and 2, what do they become? Well, if x is equal to 0, u is going to be 0 also. Let's just write it like this, u of 0. Now that's going to be 0. And in the upper limit of integration, if x is equal to 2, the u is going to be 4. And so all of this becomes and now you see we can directly apply this result up here because the u here matches with respect to what we're integrating. And so we can write this as, notice also I pulled the 1/2 in front of the integral because it's just a constant, and so we get Now we just have to plug the 4 and the 0 in for the u, and we get and I'm putting that up here. We can simplify that as now 3 to the 4th, that's going to be 81. 3 to the 0, that's just 1. And so we're going to get and there we go. And just take note, right down here, I could have taken a little shortcut. I could have actually pulled away the constant term right here and just written this piece as and there we have the same thing as what we have up here. And that concludes this lesson on differentiation of exponential and logarithmic functions to any base.